Hello friends, let's continue our discussion on understanding the creep behavior of a material. We define creep as the time dependent behavior of the material, and since the influence of time on the behavior of the material becomes more pronounced at high temperature, this particular testing technique is used to understand the high temperature behavior of the material, or this particular approach is adapted to understand the high temperature behavior of the materials. Now we saw there are the different ways of representing the creep behavior. To illustrate the creep behavior, you can take different approaches. The conventional way usually involves, or the preferred way involves, representing creep in the form of a two-dimensional curve wherein the strain and time is considered. In order to facilitate such a two-dimensional representation, we assume that the mechanical condition that we impose on the material is constant all through the testing period, in addition to temperature, of course. So even though the material might exhibit a change in its dimension, the condition or the way we impose the condition is in such a way that the stress that is imposed on the materials remains constant all through the testing period. So we relate the stress not to the initial dimension of the material but the instantaneous cross section of the material. So that's how we ensure that the stress imposed by it on the material is constant. Now we saw in the previous lectures that the creep behavior of the crystalline material can be rendered by a representative curve which is of this form. So when you represent the creep behavior using strain and time, a trend is usually exhibited by the huge range of crystalline material, and that trend can be represented by this form of curve. So depending on the slope of this curve, we were able to section it into different stages. The reason we call it as stages is because it happens chronologically one after the other. So the different section can be referred to as the stages. And we saw that the initial stage, this stage, it is referred to as the instantaneous creep, as it just follows once we apply the load. So one primary difference between the tensile testing and the creep testing is that in tensile testing the loading progressively increases. However, in creep we immediately impose a load, and that immediate loading condition results in the instantaneous creep. And in the previous lecture we were able to relate the factors that are responsible for this instantaneous creep, and we saw that once you impose the load, the material responds by an elastic behavior, anelastic behavior, and also a plastic behavior. And combination of these three, elasticity, anelasticity, and plasticity, would be responsible for this instantaneous creep behavior. So whatever happens in this instantaneous region is predominantly due to the mechanical condition or the stress. So whatever response that a material provides in this particular section of this curve is predominantly due to the mechanical condition that we impose. Now this section, or the instantaneous creep, is followed by a section wherein the slope gradually decreases, meaning if you translate it to the testing condition, the strain rate gradually decreases for the given load, and this we refer to as the transient creep. And this strain rate, or this decrease in strain rate, we were able to understand that is because once you impose a definite condition, once there is an introduction of plasticity, for the extended application of this load, the number of dislocation increases, and with increase in the dislocation density, the propagation or the glide of the dislocation is impeded. That means the plastic deformation is restricted. So once you have a restricted plastic deformation for the given amount of load, then the strain rate gradually decreases, and this is responsible for the transient creep. So in the initial stages you have combination of behavior that includes elastic, anelastic, and plastic. In the transient stage, which follows the instantaneous initial stage, the plastic deformation becomes dominant. However, the plastic deformation is confined to a given amount of load. There is not much strain that is possible, therefore the strain rate decreases. So in both these initial stages, we saw the stress is the dominant factor. However, as the time prolongs within the framework of the tensile testing, the role of temperature becomes increasingly pronounced. So what temperature does is, it allows or it increases the possibility of the migration or the propagation of the dislocation, thereby enhancing the plasticity. We saw there are different ways the temperature establishes that. One is by creating the annihilation of the dislocation, the other is by rearranging the dislocation. And once the temperature was able to establish or enhance the plasticity, then you have a balance between restricted plasticity that is caused by stress alone and the enhanced plasticity that is brought about by the temperature. This balance is what is responsible for the steady state creep. And in the final stages, what we have is the increased amount of plastic deformation, primarily due to the temperature, and this leads to the increase in the creep strain rate in the final stages, ultimately leading to the failure of the material. So based on the slope of the curve, we were able to section the overall creep curve into different stages, and what we did was we took the phenomenological approach. We related each of these stages to the behavior of the material and found the factor that is responsible for each of these stages. And now we are able to see that in the initial stages, or in the first stage that comprises of the instantaneous creep and the transient creep, it is stress that plays a dominant role. In the subsequent stages involving the steady state creep and the accelerating creep, the role of temperature becomes increasingly pronounced. So we have stress playing a dominant role in the initial stages, we have temperature playing a dominant role as the time progresses. In other words, the role of temperature becomes increasingly dominant with time. So this is what we saw in the previous lecture. The influence of stress can be understood by considering the strain hardening aspect of the material, and the influence of temperature can be understood by or can be related to the common behavior of recovery to understand its influence on the creep behavior. So this is how we were able to relate the behavior of the material to the creep curve that we see. So this approach which we have taken is referred to as the phenomenological approach. Now in this section, or when we entered the previous lecture, we said that in the subsequent lecture we will be considering the overall creep curve or ways to express the overall creep curve. So that is what we will be doing in this lecture. So we have sectioned the creep so far, that has helped us to relate the material behavior to the creep curve or the different stages of the creep curve. We were able to say which material behavior was responsible for which part of the creep curve. Now we want to arrive at an overall expression, a numerical expression that would help us quantify the creep behavior. So that is what we will be looking into in this lecture. So the first assumption for arriving at such an expression is that we will be talking about material that follow such a representative creep curve. So to arrive at an expression, a generalized expression for the creep curve, we will be confining ourselves in this lecture to materials that adhere or that follow the representative curve, representative creep curve, meaning you have different slopes categorizing or characterizing the different stages of the creep. And secondly, whatever expression we are talking about or we will be talking about, it is numerical or it is empirical in nature because we derive it from the experimental observation. So the way people have arrived at this expression is they have looked into or they have collected a huge amount of data from the experimental observations, and they have fitted a plot that would encompass all the data points that they have considered. So they will plot the data that they gain from the experimental observation, and they would provide a best fitting for it, and then they would arrive at an expression. So this is not your conventional derivation, but rather a fitting approach that is based on the experimental observation. So this is largely experiment based expression. So this is an expression that is largely based on the experiments. So the first person who rendered us this expression was Andrade. and he worked on this creep problem over a little over a century before. So in the years that he worked on this problem was 1910 to 1914. So like we said earlier, the way he approached this problem was purely experimental. He did a lot of experiments on the crystalline materials, so metals and alloys. He collected the data and he fitted the curve so that the best curve would include all the data points. So that is how he arrived at this plot. Now, this plot doesn't essentially require a phenomenological approach, meaning since he doesn't know how the fitted curve would look like, he cannot easily get into the phenomenological approach of it. He cannot section the different data. But what he observed was there was two sections that was clearly visible. So for him, instead of different stages, there was two sections that were clearly visible, or purely based on experimental data, there were two sections that were clearly visible. And these sections he referred to as the time dependent sections and time development sections. So rather time independent sections and the time, so this is time independent and time development. So time based and time independent sections. So that is the two ways he categorized the creep curve. Now he followed the way of representing the creep behavior, or the approach that he took to represent his data of the creep behavior involved or followed the conventional approach of strain versus time. So whenever he talked about time independent behavior, what he meant was, for a definite period of time, when you consider a small time step dt which is close to 0 in the time independent region, so in the time independent region of the overall creep, like I said, his works was the pioneering work, so he was not at the liberty of using the different stages. So what he categorized, the way he categorized was the time independent region and the time development region. So in the time independent region, for a small time step of this categorized by this expression here, the amount of strain was constant, meaning the strain rate was constant. If you talk in terms of strain rate, since we are acquainted with it, you can use that. But for him, in this period of time, in this time dependent period, the strain over a small duration of time, a strain over a small duration of time, which is characterized in this manner, is independent or is constant for the different dt's. So if you section the overall time into different time steps, for each and every time step, the amount of strain was constant. So if you plot that, if you make that consideration and if you translate it to the constant strain rate, then this section, the time independent section plot would look like something like this, Now this we know to be, or we identify this part of the curve to be instantaneous creep. So what Andrade wanted to do was, he wanted to arrive at an expression for the overall change in the strain during the creep testing. So he wanted to arrive at an expression for the overall creep curve based on the change in strain with respect to time. And now the first stage he categorized, or the first stage he identified, was a stage which we can refer to as the epsilon naught. The strain at this stage we can refer to as the epsilon naught, which was independent of time. Even though there is a definite strain that occurs over the period of time, for a given duration there is a definite strain that is exhibited by the material, the rate of that strain is independent of time. So amount of strain that happens during this definite period of time, during this individual time step, in this period of time, since it is constant, he assumed it to be independent of time. So the strain rate in this period is independent of time, and therefore whatever changes occurs at a definite time step or a very small time step will be constant, and that's the reason why he referred to that as the time independent strain. So in addition to this time independent strain, he had other strains which we now know to be the other stages of creep, that is the transient creep, steady state creep, and the tertiary creep. And these different creeps or different strain he referred to as the time development strain or time dependent creep. Time development strain. So he sectioned the overall creep curve into time independent strain and the time development strain. Time independent creep and the time development creep. The time independent creep is characterized by constant creep rate, meaning for a small duration in this time independent region, the amount of strain is constant. Time independent creep doesn't mean that there is constant, there is no strain in this period, but there is a constant amount of strain for a small duration within this period. However, in contrast to this time independent zone of the overall creep curve, in the time development zone, there is a progressive change. He did not say that the strain increases, he did not say that strain decreases. All that he said was there is a progressive change in the amount of strain in the time development region of the overall creep curve. So even though this approach can be referred to as the phenomenological approach, that is, he sectioned the overall creep curve into, or he considered the overall creep curve as two different sections. His sections were not relevant to, or it was not as distinct as like the one that we have considered so far. So his sectioning is not as definite as the one we have considered so far. So he was not privy to the knowledge or the material aspects that are involved that we are so far acquainted with ourselves in the previous lecture. He was not privy to that. So all that he did was, based on the data, he categorized two sections, the time dependent section and the time development section. Now the time dependent section or the time independent section of his curve, which we related or which we expressed it as epsilon naught time, is nothing but the instantaneous creep curve. If you could relate this section of the creep curve, which he referred to it as the time independent region, this we have understood it, we have seen it, and we have referred to it as the instantaneous creep curve. So he saw that the best way to express the strain exhibited by the material in this instantaneous region, that is, to our understanding it is the instantaneous region, to him it is the time independent region. So the best way to express the strain exhibited by a material in this time independent region is using an exponential term. So the best way will involve epsilon exponential kappa t. So meaning you have epsilon bar. The epsilon bar is the instantaneous strain at t is equal to 0 or t is close to 0. So based on his experimental observation, rather, he understood that the best way for expressing the strain in the time independent region is using an exponential factor, and that exponential factor, or using this exponential factor, the strain over the period of time can be expressed in this manner. It is important to note that this expression is confined to the time independent region of this creep curve. And now the epsilon bar is the instantaneous strain. So the instantaneous strain is, supposing you apply a load and the instantaneous strain that occurs at the time close to 0. The moment you apply the load, at that moment the strain exhibited by the material is the epsilon bar. So this is the very first time step that it is possible for us to consider, and the very first strain that is exhibited by the material the moment you apply the load. This could represent this region here, where the very moment you apply the load, you are able to measure the immediate strain, and based on the strain, you would be able to then understand, as the time prolongs within this region, what would be the strain exhibited by the material. So if you consider a very small time step t d naught, that is immediately after you impose the load, then epsilon bar is the strain imposed at that time t d naught. And in the subsequent time steps, of course the t d naught is close to 0. In subsequent similar time step, what is the strain exhibited by the material can be expressed in this term, meaning as the time prolongs, the strain exhibited by the material increases exponentially. So that is what this expression tells us. In the instantaneous region, in the instantaneous creep region, according to the observation, experimental observation, the strain of the material increases exponentially with time. And this term here is a constant term, and this term varies conditionally, meaning when you have a constant strain rate, when this strain rate is constant, as we have seen in the instantaneous creep region, when this strain rate is constant, then this prefactor here, that is K, this prefactor here is change in the length of the material. So change in the length of the material per unit length, meaning it is something similar to our description of strain. So change in the length of the material per unit length. You have an initial length and the change in the length of the material per unit length referred to this constant. So this is a unit strain, and this definition of kappa is only when you have constant creep rate. When the creep rate is not constant, when it is not constant and it is varying with time, then this prefactor, that is K, is 0. So the way Andrade described the initial stage of the creep curve is that the creep or the strain increases exponentially with time in this stage of creep, and that expression is given here. So this expression is for the time independent zone of the creep curve. So Andrade distinguished the creep curve into time dependent and time independent and time development zone. In the time independent zone, the strain exhibited by the material is of this form. It means that during this period, the dimension or the longitudinal dimension, the length of the material or the strain exhibited by the material increases exponentially with time, and the prefactor that precedes the time here is K, and this K has a conditional description when the strain rate is constant, that is within the instantaneous creep region or the time independent region. This K here is nothing but the definite strain. However, away from this instantaneous region or time independent region, the K here is 0. So this is how the initial stage of the creep was defined by Andrade. So the first stage of the creep he characterized by the exponential increase in the strain of the material. Now the second stage of the creep, the way he expressed the second stage of the creep, so this epsilon time development creep, he expressed this using two different terms. So these two different terms involved the one that related to the transient creep and the other that related to the steady state creep. So there were two different terms that were used by Andrade, or in the formulation or in the expression that considered the overall creep curve. In addition to the time independent zone, the time development zone comprises of two terms. One term, it relates to the transient region, the other term, it relates to the steady state region. Of course, even though he was not privy or he did not refer to it as the transient region, he referred to it as a region wherein there was a decrease in slope, or he could relate it to the a significant change in the slope when you compare it to the subsequent steady state region, and that is how he was able to distinguish the one zone from other within the time development zone. So the initial stage for him was the time independent zone, and that is for us the instantaneous creep, wherein the strain or increase in strain is exponential with time. The second zone, the time development zone, comprises of two subzones, one wherein there is a noticeable change in the slope, the other wherein there is not much change in the slope. So this is how he vaguely differentiated, or the pioneering expression had this understanding. Now this transient creep, the strain during the transient creep was expressed by this factor, wherein again the strain during the creep is also dependent on the time. So there is a time dependent aspect to this strain in this period of creep, and it is related by this factor here, and this shows again a decelerating form of creep. and beta here represent the strength of the time. This coefficient here represent the strength of the change in slope or the change in strain rate. When the beta is more pronounced, that means the slope rate or the change in slope rate is also much increased. So this beta here, it is a constant that talks about the strength of the change in strain rate, the amount of change in strain rate. So we have one term that relates to the exponential increase in creep, or one term that talks about the exponential increase in creep or creep strain, and that is confined to time independent region. In the transient region, that belongs to time development zone of the initial or pioneering atoms, the expression for the change in creep is expressed in this manner. Now, once we started to categorize both the transient region and the instantaneous region as the first stage, then this expression was subsequently extended to something like this, where we had our exponential term here as well. Now, the reason for this extension is because in the subsequent eras, the instantaneous creep and the transient creep was categorized into stage 1 as we have seen earlier. Now, the instantaneous creep has this format wherein the strain increases exponentially, and the transient creep is of this format wherein you have a decelerating slope that is characterized by this particular relation. Now, since we have combined subsequently after the proposal of after the expression given by Andrade, we have then combined the transient stage and the instantaneous creep. The recent expression for transient creep would be of this form. The recent expression includes the original approach of Andrade and the new inclusion, because the transient creep is part of the stage 1. However, when you consider this description of the constant K, which shows that this is 0 when the strain rate is not constant, and since in the transient creep region the strain rate is not constant, it ultimately leads back to the original description. The reason we would like to include this here is because to indicate that even though this is separately treated, this forms a part of the stage or the initial stage of the creep behavior or the stage 1 of the creep behavior. However, despite this inclusion here, it does not play a much role because of the specific definition of the constant K, and ultimately the change in strain during the transient period over or with respect to time is described by this expression here. So, in the instantaneous or time independent stage, the change in strain is expressed by the exponential increase in strain with time. However, in the transient period, it is expressed by this relation. Now, the final stage of the time development period is the steady state stage. So, this represents the final stage of the time development period. So, in this stage, what you have is a more or less constant slope or more or less creep rate, or more or less same creep rate. So, that means if you go back to this description here, this is nothing but change in the strain or the change in the length of the material for a definite period when the slope is constant or when the strain rate is constant. So, assuming that even though you can arrive at and fit an expression differently, assuming that the slope is constant in the steady state condition and there is a constant that describes the change in state or change in strain for a definite period of time, when you multiply this constant with the time taken for the steady state creep or the time taken by the steady state creep, then this represents the overall steady state strain. So, what we have is we have a term that is K that represents a definite change in the dimension of the material during a period of time, and when you multiply that definite change in the strain of the dimension of the material during the period of time into the overall period of time, then you end up with the overall strain during steady state condition. So, this time is for the steady state condition. So when you multiply, when you consider a time period within the steady state condition or within the steady state stage, and you multiply it to the k, which is nothing but the definite change in the dimension of the material over a particular period of time, then you end up with an expression for the steady state creep or the amount of strain in that period. So ultimately, now you have your expression for creep over a period of time. So you can have an expression for strain over a period of time, which includes now the transient creep, or rather the instantaneous creep, which is independent of time, and you have your expression for the transient creep, which belongs to the time development zone, and steady state creep, which also belongs to the time development zone. And ultimately, the tertiary stage is not included in this expression because the failure of the material is so quick to warrant an inclusion. So whatever experiments that he did, or the experimental observation that he made, showed that the stage after the steady state creep is so fast that it cannot be adequately included in this expression. So whatever Andrade has done is, he has considered, or he has sectioned the overall creep into two different stages. The first stage is the time independent region, and the second stage is the time development region. So in the time independent region, we saw this relates to our instantaneous creep region, and in this creep region there is an exponential increase in strain with time. So this is how he expressed the time independent creep, the creep during or strain during the time independent region, and it is characterized by an exponential increase in the strain at this period, and the amount of increase does not vary with time. For each and every time step, that is dt, the amount of strain would remain constant, and that is the reason why it is referred to as the time independent region. However, when you consider the overall strain, there is an overall strain during this period. It does not mean there is not much strain in this period, but there is a strain in this period, and this strain is referred to as the or this strain is expressed by this expression here, wherein there is an exponential increase with time. The second region here is referred to as it considers the transient region, and this transient region, as we have seen, is a region wherein, or this we have categorized into or categorized as the stage 1 of the creep, and here there is a decelerating strain, and it is expressed in this manner, wherein with time the amount of strain decreases, and this is how it is expressed, and the degree of decrease is encompassed by this prefactor beta. And finally, when you assume a stage where there is a constant creep rate, and in that stage the amount of strain exhibited by the material for a definite period of time is given by kappa, and this is specific to the steady state condition, and when you then multiply this specific strain exhibited by the material in this steady state period over the overall period of time, so we have instant changes in strain that is assumed to be constant, that is more or less constant. Then you consider the overall period of time during which this small constant strain is exhibited, and you multiply it with the overall strain, then you finally end up with an expression of that accumulates or that calculates the overall strain in that period, and that is how you translate or calculate the steady state strain. So ultimately, the expression for the strain during the creep test is of this form. So let me rewrite it here. So the expression for the pioneering expression for the strain with respect to time comprises of three terms. So the first term, it shows that in the initial stages there is an exponential increase in the strain. The second term, that talks about the decelerating strain by including a prefactor and relating the time in this form. And finally, you have a steady state condition wherein the strain rate is more or less constant and the unit or a definite amount of strain for a particular period of time is expressed by this constant here. And when you multiply that with the overall time during which the steady state condition is exhibited, then you will be able to ascertain the amount of strain during that period. So this is how the first expression that represents the overall creep curve looks like. So far what we have done is we have considered only the section of the creep curve. We have sectioned the creep curve based on its slope or the strain rate. We have studied it individually. We have found the material property or behavior that is responsible for each of these sections. But now we saw that Andrade was able to arrive at an overall expression that can give you the amount of strain in any period of time. You can substitute any time here, then you would be able to calculate the overall strain. Now this he was able to do by sectioning the overall creep curve into two parts. The first part was a time independent one, and in this part there was an exponential increase in strain. So this is how we categorized the first part. Here the strain rate was constant. The strain exhibited by, or the small strain exhibited by the material was independent of strain, or independent of time rather. For the small amount of strain with respect to dt was constant in this region, in this time independent region, and he also observed that the length of the material or the strain exhibited by the material increased exponentially in this time step, and that is what he referred to as the time independent region. And this is what now we call as the instantaneous zone or the instantaneous creep stage. And the subsequent stage or the transient creep stage he expressed in this form, where there is a factor that quantifies the amount of decrease in the strain and its relation to time is of this form 1/3. So this is how the transient creep is characterized. And finally you have the steady state creep condition, and in this condition this also assumes that the creep rate is more or less constant. And since we have already introduced a term that denotes the instantaneous strain exhibited by the material or the strain exhibited by the material under a condition something like this. So this is only valid when you have a constant creep rate condition, and under this constant creep rate condition you have a term that describes the amount of strain exhibited by the material, and when you multiply it to the overall time period, then ultimately you can calculate the overall strain exhibited by the material during this period. And that is what we have, and that is what we include in this term. We have a strain in the overall, during the overall steady state condition. So by including all these different sections or all these different terms, that helps us quantify the amount of strain in a definite period of time that belongs to a particular stage. We have an overall expression that helps us quantify the amount of strain during the creep behavior. So even though this does not explicitly follow, or this does not have an explicit understanding of the different stages of creep, this is purely based on the experimental observation, and all these were based on the best way to fit the data. And this is a cumulative expression that helps us understand or helps us quantify how much a strain of a material would be during a creep test. If you don't know in which stage it is, you can use this expression and calculate the overall strain of the material during the creep testing. So even though outwardly it takes a phenomenological approach, the ultimate expression is an overall expression that is not confined to a specific stage. So this expression generally categorizes the overall creep into two stages. There is an exponential increase in time, and there is a decrease in the strain during the time, the amount of strain during the time, and finally there is a constant increase in strain over a period of time, and subsequently you have arrived at this expression. So this is just to take a detour from the phenomenological approach and give you an expression for the overall strain. So in the subsequent lectures we will get back to the phenomenological approach and try to understand the different creep mechanisms and try to understand the factors governing the, based on it we will try to understand the factors governing the creep. So let's see ourselves in the next lecture. Goodbye.